Okay, I believe we're live. Let me just make sure that audio and stuff is working. Hello everyone. Yeah.
Okay.
All right, we're live. So, welcome back. This is the third part of this whole lecture thing where I review my physics lectures from my mechanics class in college, freshman year. Go back to the previous two videos to see what you missed. Today we're sort of continuing where we left off last time. There, yeah, there is a playlist on my channel. I believe it's in the description. I could be wrong, but okay, yeah, no, it's not in the description of the video, but I'll put it there at some point. Today we're continuing where we left off last time. So last time we left off, and we proved that velocity is like the derivative of position. So if you have like a function that describes position, we could call it, um, maybe f isn't the right thing. We could call it r, which will be a vector of x, or of t, rather. So I'm getting back into the physics mindset. I just did math homework. So r of t would be like position. It could be something along the lines of 3t. That's your position. Or rather, if it's going to be a vector, it might be something, it might look something more like 3t I plus, let's say 4j plus 5k, where I, j, and k are unit vectors in your three-dimensional plane, like that. That's a terrible three-dimensional plane. Um, Three-dimensional plane, something like this. So where I, j, and k, this would be I, this would be j, and this would be k. But anyway, that's just a brief review of how we describe our vectors. So position would be a vector in that case, and then we could describe velocity, v of t, which will also be a vector, equals dr over dt. So it's the derivative of position with respect to time, is what this means. If you don't know calc, that's okay. I don't know too much calc myself, but I'll try to explain the different calculus concepts as best I can. Today we're going to continue with this idea of derivatives. We're also going to introduce integrals. We're going to use these ideas to understand certain systems, like a spinning wheel is a crazy system that we have to understand because, I don't know, whatever. My professor is doing a weird order of things, but anyway. So we're gonna continue this idea of derivatives. We're gonna introduce the integral. I won't be able to explain the integral too well. I'll try my best. I won't go through a very large explanation of it. I recommend you check out 3 Blue 1 Brown's video on integrals. Type in on YouTube 3 Blue 1 Brown integral and watch that to get an understanding of integrals, to really intuit it. I'll try to teach what I can depending on time and such. I don't want to spend too much time. So let's get right back into the content. So last time we proved, I'm gonna undo all that. Last time we proved that the velocity would be a derivative of position, okay? And we proved that using a limit. So we don't want to do a limit every time, especially since certain ideas of position will get really complicated. Like imagine if position was some crazy thing times I hat plus some crazy thing times j hat, all of which is respected to t. Like it would be a really annoying thing to do a limit. So very often we'll use certain. Well, first let's give an example of a fairly simple situation where imagine that I'll go to another board. Imagine that your x position, we'll do one-dimensional motion for a second, so this will just be a scalar. Your x position, your x component of your position vector, if you will, equals some constant a times t to the power of, say, n, where n is in the set of integers. So n has to be an integer. I'm not dealing with fractions and all that jazz. So this is your equation. Sorry, this is your equation for um, your x position. If you want to find out the velocity, so that would be something like vx, the velocity in the x position, that would equal n a to the power of t, n a t to the power of n minus 1. Okay? Notice what we did was we took the exponent for t, our variable in this case. T is the only thing changing with respect to time. T is time. A is a constant. So we took our exponent in our variable and we brought it to the front, and then we decreased it by 1. And this should make intuitive sense for certain things. So imagine that x is constant. X is constant. That would look something along the lines of x of t equals a. So basically, it's not changing along with time. So if something is not changing, if the position is not changing, bro, do you remember me? I do remember you. Welcome back. So if your position is not changing with respect to time, that means that the velocity should be 0, right? So we would expect that v of t to equal 0, right? And lo and behold, I'm going to just erase some stuff. Lo and behold, when we do this notion of the power rule, we get that exactly. So the power rule again is that in abstract terms, if you have a function f of x equals x, equals x to the power of n, then f prime of x, the derivative of f of x, equals nx to the n minus 1. So we could understand our function here as, we could actually understand it as x of t equals a times t to the power of 0, because anything raised to the power of 0 is 1, so it's just a. So these two are identical, they're the same. So if we use this power rule to get the derivative of position, which is velocity, we would get v of t equals 0, because we're bringing this down, 0 times a times t to the negative 1, which would simplify further to v of t equals 0a over t. But since we have a 0 in the numerator and it's being multiplied by a, this all comes out to f of v of t equals 0, and that's exactly what we would expect. So you see that the power rule works in this particular situation, and you could prove it in your own time, but we're not going to do that because this is not a calculus class. And also I don't know how to do it, so that's why we're not going to do it. Okay, so now that we understand that very helpful rule, this is derivative. Yeah, it's differentiation. So the derivative of position is velocity, kind of intuitively, because the derivative of something is the slope at that point, and velocity is the slope of your function of position, right? Okay, so now that we understand that rule, and that's going to be a very helpful rule, that's the power rule, let's talk about some other rules. So we have another rule called the sum rule. And sum rule is very simple. It's the derivative with respect to time, I guess we'll just say with respect to time for right now, of some function f of t f of t plus g of t. So funny, I'm such a cutie pie. I'm looking at my notes and I'm seeing some errors in the notes, but it's very cute. Okay, so if we have some function f and g that both have a variable t, and you want to find the derivative of f plus g with respect to t, you can actually break them up. So that would be the derivative, the derivative of f of t over dt plus the derivative of g of t with respect to dt with respect to time. So this is the sum rule. You can also prove this in your own time. I'm not going to get into that right now because, like I said, this is not a calculus class, but remember, this is the sum rule. It's a very intuitive rule, honestly. When you have a function that is the sum of two different functions, you can break it up into those two different functions and get the derivative of both of them. So that is the sum rule in short. Great. Let's move on to another rule of derivatives called the and by the way, the sum rule should also help you intuit what the subtraction quote-unquote rule would be. You would just, if it was the f of t minus g of t, it would be this minus instead, right? So plus or minus, and it goes back and forth, because when you have addition, you also have subtraction. Okay, so now let's do another rule called the product rule. Yeah, called the product rule. So the product rule says this: if you have d with respect to dt of, and remember, when you do multiplication like this, in fact, I'm going to do parentheses because I understand parentheses better. When you do multiplication, it's just going to be d of that over dt, because it's just multiplication. So when you have that of f of t times g of t, now this one is less intuitive. This equates to d with respect to dt of f of t times g of t, non-differentiated. So yeah, it's this differentiated with that, so non-differentiated, plus, in fact, you know what, I shouldn't write the f of t, I should just write f, so d of f over dt, plus d of g over dt times f of t. So in words, you take the derivative of one of them and multiply with the other function, and you take the derivative of that other function and multiply with the normal other function at time t, and you just add them. When it's multiplication, when it's division, you would subtract them, right? Because division is the inverse of multiplication. So there you go. Those are the two main rules of derivatives, and I hope that that makes sense. I'm going to clear this. Okay, I'm going to go over here. I'm going to clear that. Clear this. So I'm just clearing my whiteboard. So now that we know these different rules of differentiation, we can move on. Back to physics. Let's go back into our physics world. So that was a little break into math, although we didn't prove anything, we just declared some rules that you can go and research on your own time and prove them for yourself. I think that I, at one point, proved some rule. I didn't do it, I researched it and understood the proof, but I forgot a long time ago. Okay, back to physics. So let's declare this, let's get a better handle on this whole derivative idea. So if you have some position r, and imagine this to be a function with respect to time, and you can say this vector in terms of the x component of r, so r sub x times the I hat. We've seen this before, this notation, r sub y times j hat, and r sub z times k hat, right? We've seen this notation. So we could express velocity in a very similar way, not in, but based on position. So v, the velocity, would equal r, okay, the derivative of rx with respect to time, because that's what velocity is with relation to position, it's in respect to time, times I hat. Now notice that you are taking the derivative of this whole thing, right? We are taking that entire derivative, but since I hat is constant, it doesn't change with time. We just bring it down as a constant, and we just take the derivative of r sub x, which may or may not be changing with respect to time. We don't actually know. What happened here? Oh, there's just a thing. Okay, so it would be that plus, again, you should be able to understand where this is going, the derivative of r sub y with respect to dt, plus the, is this as small as it gets? Yes. I just wondered what that did. Okay, plus the derivative of r sub z over dt times k hat. Oh, and I forgot the j hat. J hat's important. Okay, so that would be velocity, right? It's the derivative of position. It's a mouthful. Just the word derivative is a hard word to say. Okay, so next we can also have acceleration. And acceleration, maybe we showed it in the last video, I don't remember, but acceleration is also a derivative of position. It's the double derivative of position, which also makes it the derivative of velocity. So the way you would write that is our acceleration vector would equal d r sub x squared. I don't know why, or rather no, it's not. No, I'm sorry, it's yeah, I never understood where the squares go and why. But d squared r sub x. So it's the double derivative. It's the derivative of the derivative, so it's dd, I guess is what they're trying to say, over dt, and the t is squared now, because that's just how it's written, times I hat plus d squared ry over dt times j hat plus the derivative squared r sub z over dt times k hat. And it should be fairly obvious why acceleration is the derivative of velocity, because if you say, because the old idea is that velocity equals acceleration times time, and so clearly the slope of velocity is your acceleration with respect to time, right? And that's exactly what a derivative is. It's the instantaneous slope, which itself is a paradoxical oxymoron, but whatever, it works, because calculus. Okay, great. So now this is our fundamental idea, that acceleration is the double derivative of position, and the velocity is the single derivative of position. So let's actually use these ideas to understand something. So I just turned 2 pages at once. Yeah, I did. Okay, so we're going to use these ideas to understand something, and we're going to use them to understand a certain kind of motion. Now, why are we understanding this kind of motion? I don't know. I don't know, but we're doing it. Okay, suppose we have a circle. Suppose we have a circle. I'm going to try and draw a better circle. Great, that's a fine circle. And the circle has a certain radius. So let's actually color this in red. This is the circle's radius. And the radius is r naught. We're going to call that r naught. So simply r0. So let's write that up here. R naught. Just to keep track of what variables that we're given. So we're given r naught. We have r naught. We know the radius of the circle. Imagine we're considering a point, a certain position. So just first of all, we can imagine our, hold on. We can obviously say that this is our y-axis, and this be our x-axis, right? So this is only going to be two-dimensional. We know that this will be two-dimensional. So imagine we're considering a point, some position that is flying around our circle, and I'm going to call this position r, and it will be a vector. It's literally a position, and I guess the origin would be over here. Is what I'll guess. So imagine we have this vector position r, and the r, the vector r is flying around our circle with respect to time. It's in motion. You could also make that as an idea that the wheel is spinning, but I'm just going to think of it as a particle flying around a center. That's how I prefer to think about it. So we can actually write an equation for our position, and this is a very universal idea. So imagine it's going around with a fixed angular velocity. And angular velocity is said to be omega. Like we always call that omega. So imagine we're given omega as well. So we can create a function of our position like this. That position equals the cosine, or sorry, hold on, I should really put the thing. So it's going to be r naught times, I'm going to write that in white, times the cosine of omega times t. I don't have enough room here, and I also don't have a selection box to move things around. That's unfortunate. So we'll just write it like this. Ooh, I don't want to do that close parenthesis yet. I want to have this big parenthesis over here. Plus the sine of omega times t. And now we close it. So as you can see, this is the x component of our position. This is the y component of our position. And this is the radius, and we're multiplying it by the radius. If you know trigonometry, this creation should make some sense to you. But of course, I forgot one very important thing, that so far everything we've written is a scalar, right? All we've done is write a bunch of scalars, correct? This is a scalar, this is a scalar, this is a scalar, but we're trying to get a vector, right? So something doesn't make sense. So we're going to have to add this idea of vectors into our equation that honestly I should have done, but I forgot to do it. And we're going to simply do that by saying this. If cosine omega t is our, sorry, hold on, let me just erase this line. If cosine omega t is our x component, then to make it into a vector notation, we would add, and I'm actually going to make this the same as that, we would add our I hat there. So it's that scalar times I hat times the r naught scalar. And then the y component would be sine omega t, so we're going to add our j hat over here. And so now we will get a vector back for our position. So great, so we have our position modeled. Now what if I wanted to find out velocity? That's the question. So I'm gonna see if we could figure out velocity. Let's make, oh no, omega's already, yeah, omega is our angular velocity, I suppose, but imagine I want to find out the velocity of our actual location, our particle. So we can do that quite simply by taking the derivative of position. So if we recall that velocity equals dr over dt, then we can use that. So let's use that. Should I make it on another board? I don't think I'm going to make it in another board, so let's just do it over here. So velocity, okay, how do we take the derivative of this situation? Well, we can ignore constants, basically. They're not going to be derivative-ified. So the r naught is going to be left alone, the j hat and the I hat are going to be left alone, they're all constant. We only have to worry about cosine omega t and sine omega t, because these values change with respect to time, and we're looking at the derivative with respect to time. So let's take a look at that. What did I erase? Okay. How do we take the derivative of cosine with something inside? So this is another rule that hopefully you know, or you can either prove for yourself. But the derivative of cosine is negative sine, and the derivative of sine is cosine. You could plot these on a graph, and you could actually see that the slope of sine is cosine, and the slope of cosine is negative sine. But one rule to remember is that not only do we have to take that derivative and change cosine into negative sine, we're also going to have to take the omega and bring it outside for both of them, and also keep one inside. It's like a whole to do. So let's write this down. So we're going to keep our r naught as itself. R naught didn't really change. Times omega times omega negative sine omega t, which we'll just quickly understand where we're going, and I'm going to put the negative over here. So negative omega, and then sine of, and important to remember that omega will still be there, omega t. So the omega both came out and stayed in. It's like the whole thing. It's a whole production. Oop, no, I don't want that. I want white, please. Thank you. Omega t. So now the cosine turned into that, but we have to always remember our I hat. So even though this is now sine, which is normally the y projection, it's still I hat, because this is still our x component. This is now the x component of velocity. So I hat plus, oop, no, I don't want yellow, my bad, plus, and this will become omega, because it's going to come out again, but it's not going to be negative. It's still going to be positive, because the derivative of sine is just normal cosine. So omega cosine of omega t times j hat. We have to remember our j hat, because this is still the y component of our situation, and end it off. So now we've found velocity based on position. So we know the velocity of our particle now. And of course, the r naught is still involved just to scale it up properly. So this is going to be like basically the positions. Ooh, what did I do? This whole thing is going to be the position, essentially, and this will just scale it up to the proper amount, because it's r naught, because the circle has a radius of r naught. Now, one way that we should realize that we could actually still write this is, yeah, we can actually say that this equals r naught omega times the negative sine of omega t. I'm just going to quickly make those parentheses. So omega t, and then the I hat, plus, and yeah, no more omega, so cosine omega t and j hat with the parenthesis. And I actually have to put the omega t inside, so here we go. Omega t. Okay, so all I did was take this omega and just bring it out, so that now it looks a little bit better, and we could understand this a little bit better. So yeah, funny enough. So what are the things that are interesting? Well, first of all, it's clear that velocity is impacted by omega, just like position is impacted by omega, and that makes sense because omega is the angular velocity. It's how quickly the circle makes its turning and about and whatnot. Yeah. And so that impacts our velocity, but the velocity is affected by omega twice, you could say even, and also scaled appropriately, just like our position. So those are some interesting ideas. Yep, okay, fine, there you go, that's velocity. Now we can actually ask something interesting. Based on this whole idea, oh, this was still that thing. Let's go to a new board. Based on this whole idea, let's ask a question. What angle is velocity making with position? So I'm actually gonna hold on, color code these as well. So velocity was in green, I believe, and position was in what, yellow? Yellow. So what angle is the velocity making with the position? So that's a simple question. If let's look at our circle again. If the position is over here, does velocity look like this, like this? Why can't I draw like this, like this, like this, like this, like this? What does velocity look like with respect to position? I actually realize now that the entire production is a little bit deceiving because I should show that this is a vector coming from the center. That position is a vector coming from the center. So what angle is velocity making with position? Well, we can find that out. We have that tool. So a great tool to find out, oh boy, this is a whole production. Yeah. Okay. Hold on, let me just take a look at this, just to refresh myself how this is done. So one great tool that we have is we have the dot product. We know that I'm not going to do x. X is a bad name. A dot B equals the magnitude of A times the magnitude of B times cosine of theta, right, between the two things. And we also know that A dot B equals A sub x times vector I plus, A sub x, so the x component of A times B sub x times I plus A sub y times I times B sub y times I. And this is actually a simplified form of the more complicated idea. So let's use the dot product. We can use the dot product in our case. Let's erase this and make it more what we're trying to do. Okay, so let's find out what the dot product is between R and V, and we're going to take the dot product between them. So what would this look like? Well, if we remember that R is, oh boy, it's a whole thing. It's R naught, and I'm just going to color code this as position just to remember that this position is R naught times cosine of omega t I plus sine of omega t times j, right? Okay, so it will be that's our R, dot, and then the velocity is R naught times omega times the negative sine of omega t, that's the I hat, plus the cosine of omega t, and that's the j hat, that's the y component. Okay, well, these guys are scalars, right? so we don't have to do much about them. This is just basic multiplication, so we don't have to think too much about them, except to multiply them. So that's going to give us, and I'm going to, what color should I use? I'm just going to use white. So that's going to give us, actually, you know what? I'm going to use white. I'm going to use white. Okay. So that's going to give us that it's just R naught omega squared, right? Because it's R naught, no, I'm sorry, backwards. It's R naught squared times omega. My bad. Um, okay, and then we have, so we could just FOIL these terms now, is something that we could do, right? Does this make sense in terms of math? Because it's all multiplication anyway. And yeah, we could just FOIL these terms and multiply with that. So cosine omega t I hat times the negative sine omega t I hat. Well, we know that these are vectors, right? This term and this term are vectors, correct? Because they have the I hat. And so when you're doing multiplication like this, these need to be a dot product, okay? So the dot product will involve cosine of theta. So what is theta between I hat and I hat? Well, theta is 0 because they're the same vector. So the angle theta made between them is the same angle. So that will give us just straight up, it's going to give us a scalar, right? So we know that it's just going to be cosine omega t times negative sine omega t, because this is a scalar, and this is a scalar, which tells us that these are the magnitudes of our respective vectors. And that, in fact, it won't actually be 0 between these two larger, okay, the angle, sorry, hold on, let's back up. Let's back up. The angle between these two larger vectors is not going to be 0. The angle between this big vector with the I hat and this big vector with the I hat is 180, because this is negative. So it will look like this. Like these are our two vectors, and so the angle is 180. Now fortunately, that's just negative 1. So it's negative 1, that's our cosine theta. Right, negative 1 would be our cosine of theta, because cosine of 180 is negative 1. So that's going to give us, I'm just going to back all the way up. So that's going to give us negative 1, that's going to give us negative 1 times sine omega times t, because that's the magnitude of our first vector, times cosine omega t, because that's the magnitude of our second vector, times negative 1. So let's write that all. Negative 1, so that's just a negative, cosine omega t, that's the magnitude of our first vector, sine omega t. I hope that that made sense how we got this term, because I hope that made sense, because it's the dot product between these two vectors. The theta is 180, meaning the cosine is negative 1, and then it's the magnitudes times each other, which are these two things, and so that's that first thing. Okay, so that was that. Next we have cosine omega t I hat times cosine omega t j hat. Well, in this case, I hat and j hat are perpendicular, right? So cosine of theta is cosine of 90 degrees, which is 0. So we could just forget about these terms being multiplied with each other, because that's just going to be 0. So then we have to worry about this term and this term. And again, it's j hat and I hat, so that's also going to be 0, so we don't have to worry about that. And now we have to worry about this term and this term. And in this case, it's going to be a similar situation. It's not negative because it's normal, there's no negative here, and so it's straight up 0 degrees is the angle, so cosine is 1, so it's sine omega t times cosine omega t. Okay, plus sine omega, so that's theta, sine omega t cosine, I'm running out of room, omega t. Yeah, that's fine. That's fine. So, and that is all going to be inside of our massive parentheses over here. Okay, so this is our dot product, and so far we've eliminated all the vectors. So now all we're dealing with is scalars at this point, which is great. So we could just evaluate all these things. Now the question is, how do we evaluate all these things? It's a wonderful question. if you notice, we don't have to do too much evaluation. It's just sine omega t cosine omega t minus sine omega t cosine omega t, which is just 0. So all of this simplifies to r naught omega, so r naught squared omega times 0, which equals 0. So we know that the dot product between our two vectors is 0. Now we use some basic understanding. We know that the magnitude of our position is not 0. The magnitude is like r naught, and if r naught is 1, then it's 1. And if it's 0, then it is 0, so that's fine. We know that our velocity, the magnitude of it is not 0, because it's scaled up based on r naught as well. And you can't have, so this being our velocity, if this term is going to be 0, then just by virtue of sine and cosine, this term won't be 0, and then it will be multiplied by r naught and omega. That's the whole thing. Now, if omega is 0, then yeah, our velocity is 0, but that's a different story. So great, so we know that the magnitudes of these two vectors are not equal to 0, but yet the dot product between them is equal to 0, which means that the cosine of theta between these two vectors equals 0. That's the only way to get the dot product equal to 0. It's going to look something like the magnitude of r times the magnitude of v equal times cosine of theta equals 0. And the only way for that to be true is if cosine of theta is equal to 0, which means that theta equals 90 degrees. Because the cosine of 90 degrees is 0. Which means that we can go back over here to our circle drawing, and we can actually draw what velocity may look like. Velocity will be perpendicular to position. So this, in fact, you know what, I'm gonna erase this, and I'm gonna put it over here. Right, that looks a little bit clearer, I think. And now we can draw our velocity, and the velocity will look something like this. It's perpendicular to our position. And this is one idea they may have heard, that when something is flying around in a circle, the velocity is always perpendicular to the position, which is pretty cool. So we just proved that using our understanding of vectors and dot product and all that jazz. Okay, moving on. What about acceleration? So what color didn't I use yet? Did I use blue yet? No, I used blue for omega. I should have just kept omega normal. So what about position? I mean acceleration. Let's make acceleration, I don't know, purple. That's fine. So what about acceleration? Well, acceleration equals the double derivative of our position. Hold on. Equals the double derivative of our position with respect to time. I'm going to have to expand this thing every time, huh? Can I just click U, please? Yes, okay, good. Over dt. It also equals the first derivative of our velocity with respect to dt. Correct? With respect to dt. So all we have to do is take the derivative of our velocity and we'll get acceleration. So acceleration equals, and I'm gonna write all the constants as white. R naught times omega, right? Or R naught squared times omega, because that's what we had as constants for our velocity. Where did we prove velocity? We proved it over here. Oh, so it's not R naught squared, I'm sorry, it's just straight up R naught omega. So those are constants, they won't be derivative-ified. 4, yeah, so sorry, hold on, it's just R naught omega. And then again, it's what's inside of the parentheses, the negative sine omega times t and the cosine omega times t with respect to I hat. So the I hats won't be derivative again. So what is the derivative of negative sine? The derivative of negative sine is negative cosine, I think. Yeah, if the derivative of sine is cosine, then the derivative of cosine is, if the derivative of sine is cosine, then the derivative of negative sine is negative cosine. And we can't forget that we have to bring the omega out again. So we're going to have a negative omega cosine of omega t times our I hat. So now cosine is back to I hat. And this makes sense because we're looking at, right now we're looking at this part. And so we bring the omega out, we change the sine we change the negative sign to a negative cosine, and then what it's ever left stays the same, and the I hat is just sort of there. So that's cool. And that plus, or rather minus, over here, what do we have? We have cosine, and the derivative of cosine is negative sine, correct? So we'll have minus omega sine omega t. Yeah, so minus omega sine of omega t. J hat. Don't forget the j hat. So that's our acceleration. Now again, we could bring out a negative omega. We could bring out a negative omega. So that means that acceleration in all of its glory, acceleration equals negative, because we're bringing out a negative omega, negative r naught omega squared times no, not omega, we brought out the omega, times cosine of omega t, right, with I hat, plus sine omega t with j hat. J hat. Okay, yep, that makes sense. So all we did was bring out a negative omega. Now, this part should look familiar. And I'll actually underline it with a specific color. This part and this should look familiar. We have r naught times this little creation. That looks shockingly similar to our position. Remember, our position was also r naught times cosine omega t I plus sine omega t j, right? So this means, if you look closely, you can see that this is true. You don't actually have to look that close. We can rewrite this as, this equals negative omega squared, and I'm actually going to write this in a different color, just to show, times r naught times cosine omega t I hat plus sine omega t j hat. This whole thing equals our vector r, our position. So that means, just intuitively, not intuitively, this is very not intuitive, but this means very incredibly, I should say, that acceleration, our dear friend acceleration, equals negative omega squared, so it's based on negative omega squared, times our position vector. Bum, bum, bum. That is crazy. So it's proportional to our position, which is shocking, and it's proportional to omega, which is more understandable, but yeah, pretty crazy, no? I think that's pretty crazy. Okay. So, yeah, that's pretty insane, I think. Now, one thing that's pretty awesome as well is, I should note, omega squared is a scalar. Okay, right? It's a scalar, it's just a number. Which means that you could actually envision this. Imagine omega is just 1. You could envision this as acceleration. Oh boy, that's terrible. That does not look good. We've been seeing acceleration as purple for all this time. I can't stop. Which means that acceleration, you could view it as being equal to negative r, or proportional to negative r, if omega is 1. So yeah, omega is proportional, I suppose, is what you would write, to negative r. Which means it's proportional to r, but it means it's also like the reverse of r. In terms of orientation, it's flipped. So that means we could go back to our drawing, and we can make something very cool. We can show that this is acceleration, right? it's backwards. It's flipped. It's r flipped and also scaled according to omega and a few other things. It's actually no. It's vector r flipped and scaled with negative and scaled with omega squared. The flipping was the negative part, right? So it's r flipped and it's r flipped and scaled with omega squared. There you go. That's the statement. Acceleration is our vector r flipped and scaled with omega squared. Hold on, someone's knocking at the door. I'll be right back. I'm in the middle of streaming, by the way. Streaming? Yeah. It's just my roommate. He didn't have his key. Let's continue. All right, so we found out that acceleration is our vector of position flipped, scaled with omega squared, which is pretty cool. Okay. Now let's really get into some craziness. Oh boy. Let's see if we could find. Oh boy, I can't write. Find our vector r. So you know what? I'm gonna stay color consistent. Find r. Find position. Given. And I want to stop writing acceleration as purple because it's annoying. So I'm just gonna change it to blue. Acceleration. Given acceleration. So find r given acceleration. So how do you get position from acceleration? Okay. My professor didn't go through this at all in detail, and I think that I will. I think that I'm going to go through it. So, imagine, let's think about one-dimensional motion. So this is x, which is distance. So I'm actually just, you know what, I'm going to say r, just to be consistent. So this is r sub x. It's just one-dimensional motion. So this is our x displacement. I'm only thinking in one dimension for now. And this, I guess time will be in red. We could make a graph of our position. Imagine it looks something like, I don't know, yeah, this. So this is a whole, this was actually a bad idea. I should never have done it like this. You know what? Fine, I'm going to keep it like this. So this is our position with respect to time. And you know what? I'm actually going to make this whole thing on a different slide. I'm sorry. Yeah, I'm going to think about structuring this better. Okay. So imagine we have, let's make our axis again. We have time, and I'm going to stick to having position. So imagine it looks something like this. It's just a line. Okay? This means, if it's just a line, it means that our velocity is constant. Okay? So imagine this is like 5, and this is, I don't know, also 5, and this is, and then down here we have just 0. So in 5 seconds, we've gone 5, sorry, I got used to writing the vector part. It's just normal that. We've gone 5 meters, okay? In 5 seconds, we've gone 5 meters. That's another way of saying we've gone, and since it's a line, it means that during these 5 seconds, we were going 5 meters per every 1 second, okay? So we were going 5 meters per second, essentially. So let's make our velocity graph. Based off of that information, we can make our velocity graph. So from time 0 to time 5, from time 0 to time 5, let's make this t, and let's keep consistent. This will be v sub x, right? Consistent colors, I guess. So we found out that between time 0 and time 5, we were going 5 meters per second. So let's make another 5 over here. And actually, hold on. No, I'm sorry. Hold on. I'm wrong. We weren't going, we traveled 5 meters in 5 seconds. So we were going 1 meter per second. 5 meters in 5 seconds. Okay? We were going 5 meters in 5 seconds. Cool? So that means that we were going 1 meter per second. Not bad. So 1 meter per second. So now let's go back to our velocity graph and let's do that properly. So it's not 5, it's 1. And this velocity is obviously in meters per second. And this is time. So over these 5 seconds, we were going 1 meter per second. Okay, now here's the beautiful thing. We could view our position as velocity times time. So our position r sub x equals velocity times time. This is an old idea. Okay? This, in this case, for these 5 seconds, that means that our position equals, velocity is 1, so 1 times 5. 1 times 5. The key thing to note is that interesting. Okay, that is, this side has a length of 1, and this has a length of 5. 5 times 1 is the area under this, under the line. Okay? So that means that your position is the distance you've traveled in a certain amount of time is the area under the situation made by your velocity between those 2 moments of time. The position within 2 moments of time equals the area that is made between your velocity graph, your velocity function, and the horizontal axis, basically, over that same increment of time. And this fact holds true no matter what velocity looks like. So if I make another graph, and velocity looks something like this, then between, I'm going to stick to green, between these moments of time, imagine these 2 moments of time, the position, the amount of distance you've traveled is the area. Now, since this isn't a math class, I won't go too much into detail as to how we calculate the area under a curve and why this makes sense. I recommend you go watch the 3 blue, 1 brown video about integrals. But in that video, he explains that the way to find an area under a curve is the integral. So using all this information, if we go back to our original question, find position based on acceleration. Well, the first thing we would want to do is we would want to find velocity based on acceleration. And then we would want to find position based on velocity. And since the derivative of velocity is acceleration, that means that the integral of acceleration between 2 points will be velocity. And of course the integral is the antiderivative. Not of course, but the integral is the antiderivative. How do we know that? How do we know that a function to describe the area under a graph is the antiderivative of that same function? How do we know that? Is there a simple way I could explain it? How do we know that that a function to describe the area under a line is the antiderivative of that very line? I'm not sure if I could explain it, but I know the 3 blue 1 brown video explains it, and I'll probably watch it again, honestly, after this. Let's see, can I remember how he does it exactly? No. I guess maybe you could say that the amount the area changes for a tiny amount is the actual function. The amount the area changes for a tiny amount of space, of time, is the function. Is the value of the function, which means that the amount the area changes for a tiny amount of time is the derivative of the amount the area changed. Yeah, the amount the area changed for a tiny amount of time is the function, which means that the function, this green line, our function, making up our curve, the function is the derivative of the area. And once you find out intuitively that the function is the derivative of the area, that means the area is the antiderivative of the function. Yeah, that's how I would say it. So the key is to know that our function, this curve, this green curve, or in this case it's a line, but over here it's a curve. The function is the derivative of the area, because it is at every moment of time, it is the rate of change of the area. It is how much the area changes. It's the slope of the area, if you will. And so it is the derivative of the area. And since it's the derivative of the area, it means the area is the antiderivative of the curve. And so how to find the antiderivative of something? Well, let's talk about how we find the antiderivative of something. Imagine we have a curve f of x equals x squared, then f prime of x, the derivative of x, would equal 2x. Now, how do you go from 2x back to x squared? Well, when you go from 2x back to x squared, you're asking something. You're asking what power does x have to go to, and what coefficient would we have? And so we divide this by, not itself, how do I think about this? So first of all, we're going to bring this number up top, right? That's our thing. So we're going to bring the number up top, because we know that the step before, we're trying to go from here to here. So to go from f prime of x to f of x, we're going to bring the coefficient in front of x to the top, because we know that when we went from here down, we brought it to the front. So we're just going to bring it to the top. And then what goes over here? Well, whatever goes over there, we know that the coefficient times whatever was here is equal to the coefficient in front of the x. So that means that it's just going to be 1, which is just x squared. What if our starting function was different? F of x equals 5x squared. Well, then f prime of x equals 10x squared. Sorry, equals 10x. Which means that if we want to go from here to here, we would... no, I'm sorry. We don't bring the coefficient to the top. We simply add 1 to the power that was already here. We add 1 to the power that was already here, because that's the rule. The rule is we take 1 away from here, and we move it down, and we move this whole thing down. Right. Yeah, the rule was we move the entire power down, and we also take 1 of the power, and that becomes the new power. So we add 1 to the power that's here, which makes it a 2, and then we know that 2 times our old coefficient had to equal 2, and that's how we knew it was 1. So over here, we're going to add 1 to x to the power of 1, so that will be, we're going to add 1 to the power of x to the power of 1, so that's going to be a 2. And we know that 2 times whatever was here had to be 10. And the only number that is, so you can ask, like, what was this? What was n over here? So we know that 2n equaled 10. And so we know that n equals 5. And so we can reverse the whole process and get 5 over here. Okay. Let's now that I worked that out properly in my head, or rather just now, let me explain it better. Let me explain it better. There we go. Imagine we have some function f of x equals 3x to the power of 3 plus 7. Okay? So what's the derivative of this? Well, f prime of x, using the power rule, we take the 3 and we bring it down, and we make that the new coefficient. Not the new coefficient, but we multiply that with our existing coefficients. That's going to be 9x plus 7 by itself is just x to the power of 0. So we're going to bring that in front. And so now that will just become 0. So it's plus 0. Hold on. 7x So 9x plus 0. Okay? All right, now that's the same thing as just 9x. So now how do we go from 9x, which is f prime, back to f of x? Well, we're gonna do the opposite rule. So we're gonna add 1 to the exponent, which will bring us to x squared. And sorry, hold on. My bad, I messed it up on the way down. We're gonna subtract 1 from this exponent, which will bring it down to 2, so x squared. And so now to reverse, we're gonna add 1 to the exponent, which will be x to the power of 3. And we know that 3 times whatever should go here equals 9. And so 3 times what equals 9? Well, 3 times 3 equals 9. Great. Now the problem is we lost our old buddy, our old friend. And so whenever you're actually taking the antiderivative, you always say plus c, plus some constant, because you don't know what used to be there, because whatever used to be there didn't actually affect the slope. The way the graph was shifted, imagine we have like some graph, the way the curve is shifted doesn't actually affect the slope, and so we lose that information, we lose the shifting information when we take the derivative. And so when we take the antiderivative, we add a constant. Now the way we'll be taking antiderivatives in physics is we're always going to have like a starting point and an ending point for our integral, and that will take care of the constant because they'll cancel out. Because yeah, the area. The change in area from this point to this point, I guess is what I would say. Yeah, the change in area from this point to this point is the same as the change in area from this point to this point. I guess that's true. The new area added is basically the same. And because of that, the constant cancels out. Go watch the 3 blue 1 brown video. Again, is what I would recommend. But now let's bring it down to physics, and I'll show you what I mean when I say that we'll take care of the fact that we lost our constant as data. Okay, so let's go back to our question. Can we find acceleration? Can we find position given acceleration? Well, let's take a very simple example. So let's first of all find the rule, the notation that velocity is going to equal the integral from some time to from like t0 to t1 of, so that it's going to be the integral. The integral basically means the slope under a graph of our acceleration times time times dt. And so notice how dt is with acceleration here instead of below, as it was with derivative, where it was like dA over dt. Now we're doing the reverse. We're basically taking the antiderivative. And so this will be so yeah, acceleration will take the antiderivative of acceleration. I'll write it down more, not more clear, but more expanded. This is going to be from t0, the integral, not even the integral anymore. This is going to be the antiderivative of acceleration. Yeah, it's like the change in velocity. It's really like delta v, I should say. But from time 0 to time t. But anyway, this is going to be the, I don't know how I would write antiderivative of something. I don't know how I would write antiderivative of something without thinking. Let's say that a, for now, let's say that a equals x squared, or rather t squared, because we're working with t over here as our variable. So a, and I'm not going to make it a, well, I guess it is a vector already. A equals t I hat, we have to throw the I hat in now because it's a vector. So a equals t I hat plus I don't know how to say this. plus 7 I hat. Yeah, that would be like a constant essentially. So this 7 is playing the role of our constant, and it's like, yeah, it's I hat. So we're just adding a constant vector along the x-axis with a magnitude of 7. Is essentially what 7 I hat means. I'm getting a pretty good intuition of vectors. That's pretty cool. Okay, so yeah, so now that's our acceleration. So now we take the antiderivative of this. What is the antiderivative of this? Well, actually, you know what? I'm going to get rid of this. We take the antiderivative of this to get our velocity. So again, we add 1. So the I hat is basically, we could ignore it because it's constant no matter what. So it's just going to come down again. So we're going to just put it over here, I hat. And we add 1 to the coefficient, not to the coefficient, to the power that t is at, so t to the power of 2. And we know that 2 times the old coefficient that we had is equal to 1, because there's a 1 here essentially. So the old coefficient that we had must have been 1 over 2. So this is our equation for velocity, really. Yeah, this really is. But of course there's some constant, right? We forget about the constant. So the way we take care of the constant is we restrict ourselves between these two locations, t naught and t sub 1, t sub 0 and t sub 1. And that allows us to get really the change in velocity from t sub 0 to t sub 1. I'm sorry if I'm explaining this terribly, but it's not easy to learn, and it's not easy to teach. So this is the general function plus c. To take care of the c, okay, hey dude, welcome back to the stream. So anyway, to take care of the fact that c is there, we really do 1/2 of t sub 1 squared minus 1/2, I'll do parentheses, minus 1/2 of t sub naught squared, right? Now imagine if there was a constant, so like plus c and plus c. You see that this, because the negative is over here, this would become minus c, and so that would cancel with this. So this literally takes care of our constant, and we could find the area. Again, bring this back to the idea of area. Imagine this is our axis, and this is our acceleration. This whole idea, if this is t, if here we have t sub 1, and here we have t sub 2, so we're getting our velocity, the addition to our velocity, in this amount. It's this area. And so that's really our change in velocity from the time t sub 1 and t sub 2. Yeah, and because we're doing subtraction, even if we like increase the curve, even if we shift the curve up by some constant, the fact that we're doing subtraction, that's not the same curve at all. The fact that we're doing subtraction takes care of that idea, because we get rid of the constant in general, and we get the same change in velocity. Okay, so that's how we would get velocity given acceleration. So let's actually bring this into a more concrete example. And to do that, I think I'm going to get rid of this slide. I don't need this anymore. I want to keep this slide, right? I want to keep our circle situation happy and stuff. Maybe I'll delete it actually at some point. The problem is I need it for the next lecture. Anyway. I have other slides though that I could delete. I have all those slides that showed the intuition of derivatives. So let's delete those. So yeah, so I'm gonna delete this. Yeah, I'm gonna delete that. And I'm gonna start from 5 and we're gonna move down. So let's bring this into a much more concrete example where we will find position given acceleration. So motion in a uniform gravitational field. So imagine we drop a ball. Okay. Here's our ball, and it's falling. It's falling, and there's some like acceleration on it, and the acceleration is negative g. Now negative g is a vector, but when I say negative g, what I really mean is that it's nothing in the x direction, and it's nothing in the y direction. If actually it is something in the y direction. I don't know why my professor said that. This is how I envision the 3D space. This is y, this is x, and this is z, and z is coming towards us, essentially. And so, yeah, y is down. So negative g, yeah, I'm gonna make this, yeah, we throw, I'm not looking at my notes anymore. I'm just doing this myself, because this is the last part of our lecture. So, the ball is falling because of some vector g, and I'm going to define g as follows. This is going to be so confusing. I'm going to make this capitalized because I can't do this without it being capitalized. Here's our vector g. Okay, and vector g is our acceleration, because that's what gravity is. It's accelerating. So g equals 0 I to the power 0 I hat plus.
Just let me know if you're changing it to lower.
Plus negative g j hat plus 0 k hat. Okay, and it's like so it's negative g because it's down, and I'm choosing down to be negative. So it's 0 I hat minus g j hat plus 0 k hat is our acceleration. This equals acceleration. So here's our acceleration. Now, how do we find velocity? And in fact, I'm going to make this a function of time. But of course, it doesn't change based on time. The acceleration is constant no matter what. Acceleration is staying the same throughout time. So how do we find v? How do we find velocity based on this? And then we're going to use velocity to find position. So hopefully at this point, it should be made clear that, hold on. This is so terrible. So yeah, let's find velocity. Velocity from time t equals 0. So really, this is we're finding the change in velocity from time t equals 0 till. So okay, you know what? I'm gonna do it like this. I'm gonna write it like this. It's important how we write things. So velocity at the yeah. Okay, I'm gonna choose 0 as t naught. Yeah, so 0 is like we drop the ball at time equals 0, and I want to find velocity of t. So, and t being how many seconds it's been since 0. So the velocity at times t will equal, and here we bring our acceleration in, so equals the integral from time 0 till time t, okay? Till time t, that's our t. These t's are the same. These t's are like the same t's. This one and this t are both the same. So it's from 0 till time t of our acceleration. So hold on. I want to just show that this is acceleration. So this is acceleration at times t of acceleration at time t prime. The reason why we put prime here is because I don't actually mean to put the t. I don't actually mean to put this t in here. I just mean to show that it's acceleration, which is a function with respect to time, dt prime. Okay, that's how we would write this. From 0 to t, it's the integral from 0 to t using the function of acceleration, which has t as its variable, essentially, dt. And the way we would do this is we would say that this whole idea, this whole integral, equals, and now let's really write things down with numbers. So the acceleration at time 0, what is the acceleration at time 0? The acceleration at time 0 is the same as any other acceleration. So it will be, hold on, something doesn't make sense. No, acceleration is constant. We need to find the antiderivative of it. Sorry, I forgot that we're finding the antiderivative. So 0 I hat minus g j hat plus 0 k hat. Well, 0, the antiderivative must have been Yeah, this is beautiful. It really is incredible how this works. So remember that even though acceleration isn't happening at all in the x and y directions, that doesn't mean velocity isn't happening in the x and y directions. The ball could be falling, our ball could be falling like this. So it might have started with some kind of velocity and it's just falling down because of acceleration. So we have to remember that it could have some velocity in the x and y directions. So that means that um, right, so the antiderivative of 0 I hat is going to be whatever it was at, so this is the same thing as t to the power of 0 times 0, which means that we're going to add 1 to t, so t to the power of 1, and we know that 1 times whatever was here has to be 0. So it's going to be 0t to the power of 1, which is just 0 again, but it's not necessarily 0, it's sometimes in physics equations we get two variables from the same thing. For example, s equals, yeah, if you have everything and solve for t, you get two results for t. Often we reject the negative result, but why? Because the negative result sometimes is like non-physical. It means that at time, it usually is like a value that can't exist, like a negative time. So imagine like they say you drop a ball and it falls in a parabola and you want to find its position at some time. We're not going back in time because the ball wasn't necessarily moving back in time, so it's non-physical. So we just drop that as an answer. Sorry if I didn't see that question for a long time. Hold on, I'm trying to remember how to solve for this. Because I know it has to be like, this is a 0 here, because the acceleration is 0 in the I, but I know that we have to end up with like v sub x times I, whatever velocity was in the x direction when we started. So, oh right, because we're forgetting a constant. Like again, it's gonna be like, it's gonna be, okay. So let's work this out. 0 is the same thing as is the same thing as 0 times t to the power of 1, right? 0 times t to the power of 0. Sorry, 0 times t to the power of 0. That's the same thing. It's also the same thing as 0 times t to the power of 1, or anything really. But in this case, there is no t here. So we're going to add 1 to the coefficient to the power of t, so we'll have t to the power of 1, and we know that whenever we brought 1 down, we ended up with a 0, so the coefficient was 0, but plus a constant. There was some constant that we have to remember. It could have been shifted in any direction for the velocity in the x. So we have to remember that. We have to remember its starting velocity in the x direction. So let's write that down. We have to remember its starting velocity in the x direction. So we'll say v sub x of 0 at time 0. V sub x at time 0. Right? That's its velocity in the x direction at any moment in time, really. So the velocity with respect to time equals v sub x at time 0 with I hat plus, I'm going to say plus for now, and now this is the real tricky thing. So negative g times j hat. So that's the same thing as saying negative g times t to the power of 0 j hat. So j hat's going to be the same, so we're going to add 1 to the power of t, so we'll have negative g times t to the power of 1. We know, I mean, it's not really necessarily negative g, so now we have t to the power of 1. We know that whatever we put, when we put 1 down, we ended up with negative g, so yeah, that means that it's going to be negative, so that means it's going to be negative g over 1, because negative g over 1 times 1 is negative g, so that's just negative g, so it's not going to be plus, it's going to be minus g, and now we have a t to the power of 1, so t times j hat. And this makes sense, that the velocity in the y direction would equal the acceleration in the y direction times the amount of time that's been through. So this is all making sense from what we know from our like high school mechanics, basically. So that's good. And then plus, and this is going to be the same situation, v sub z of time 0. So this is there we go. We found velocity. Um, yeah. Yeah, obviously, the whole idea of constants. I mean, we really should. Um, yeah, it's really v sub, and then it. Yeah, I really should. If we're looking for it between time 0 and time t, I should put a 0 here, and then like, yeah, I should put a 0 here, and then subtract this whole thing again, but instead of putting 0, I would put t in. But you know what, I'm going to switch this whole thing from being like a bounded integral to being a unbounded integral. We're literally just looking for um, mm, yeah, we're literally just looking for its hmm. What was it at time? No, we really should do this properly. I think I made a mistake. The y, so the let's find, yeah, okay. Let's do this properly. We're looking for 0 till time t. And we're not actually trying to find the velocity at time t. At least I don't think. No, we are. Okay. Um, so I should really write this smaller, just to have room. So let's figure out what the antiderivative is at time 0. Okay? So at time 0, it was just everything at time 0. So it was the velocity at time 0. So it was, and we don't know what those are. Those are constants. That information is not with us. So that's v sub x at time 0. This is what it means. Like v sub x of time 0. It doesn't mean times 0. I mean at time 0. Times I, times the vector I, plus v sub y of 0 times the vector j, plus v sub z of 0 times the vector k. Okay, that's our velocity. And then we subtract that with it at time t. So since the x component isn't changing with time at all, there's no acceleration here, right? So the antiderivative of that is just going to be 0. Yeah? Yeah, the antiderivative of this, ignoring the constant even, just completely ignoring the constant, is going to be 0 again. So it's 0. So 0 times vector I, essentially. Plus, this one will be negative, this one will be, yeah, we solved that this one, we solved such that this negative gj hat is the same as negative gt sub 0 j hat, and so to get the antiderivative of that, we would do t to the power of 1. Negative g over 2 would be our new coefficient, which is just negative gt, which is just negative gt. So it's going to be minus gt k hat j hat minus gt, hold on, j hat, plus, and again, this is just going to be 0 k hat. Okay, so it's that whole thing minus this whole thing. But if it's minus, then this will become a plus. And I don't want this to become a plus. Plus negative gt. If it's minus this vector minus that vector, whatever Vy was at time 0 plus gt, but I don't want it to be plus. I know that the velocity is going down, like it's accelerating down. So what does this mean? Yeah, he got He got Vy at time 0 minus. That's what the professor got. Why is it that my understanding of this isn't working? Ah! Because I'm doing this backwards. It's not this minus that. It's this minus this. No, it's not. Hold on. No, it's not. Because then this is 0. And this is not supposed to be 0. Because again, this doesn't work. I must have copied the notes down wrong. Because we're trying to get the change in velocity from time 0 to time t. Right. Yeah, no. Something is very wrong with how I'm doing this. Hold on. This guy's supposed to have a hat. These cannot be the correct values. Like, this is the one that I found for time t equals 0. And to get the velocity, they can't be the same value either, because then they'll either cancel or go too much together. And the thing is, we want them to cancel, because this formula, this idea over here, finds the change in velocity over that time. And so we would want these two to cancel each other. So yeah, like I said, this formula doesn't give us the velocity with respect to time. It gives us the change of velocity from time 0 to time t. If you want the straight up velocity with respect to time, we really do have to get rid of the bounds and just keep in mind the constants. So let's do that. Let's get rid of the bounds and keep in mind the constants. And the constants will just be whatever the velocity was at time t equals 0. If we get rid of the bounds and we keep in mind the constants, then we have that it's the antiderivative of this term, which is 0, plus the constant, which was, the constant will just say it's v sub x at time 0. And that is I hat. Plus, we want the constant of this, of the j term, which was v sub y at time 0, plus, now we want the antiderivative of this, which we found to be negative jt. So plus negative jt, which is just minus gt, and this will have a j hat. Excuse me, this will have a j hat. And then it's this plus the constant in the z direction, v sub z of 0 with a k hat. And this is an equation for our velocity. So now we have it. Yeah, now we have it. Okay, so now that we have velocity, we can get position. So let's do that. So first of all, let's clear this. And let's say that if we're given velocity, so not given, but now we have velocity at based on t equals v sub x at time 0 times I hat minus, plus v sub y at time 0 minus gt. That was the thing that we found. And then that gets a j hat, and that plus v sub z at time 0, that gets a k hat. So now let's figure out if we could find out what position is. Okay. Alright, so let's do this. We have to keep in mind the constants. So position at time t equals what? Well, it equals the x position, so r sub x, at time 0. Okay, so now we have to find the antiderivative of this. So this was the constant that we just kept in mind. So we kept in mind the constant, now we can find the antiderivative of this. So v sub x at time 0, with no t being multiplied with it, right? There's no like, so that's the same thing as saying v sub x at time 0 times t to the power of 0. We add 1 to the t to get the new power, so v sub x at time 0 times t to the power of 1. We know that 1 times, and so hold on, we don't know what the coefficient, we know that 1 times whatever the coefficient used to be is this, which means that it is still v sub x at time 0. So it's going to be, okay, so now based on what we figured out, we know that the antiderivative is v sub x at time 0 times t plus our constant. And this is our constant. So it's this plus whatever our velocity in the x direction was at time 0 times the amount of time that we've been flying. And this makes sense. The x position, our new x position is our starting x position plus whatever our velocity was in the x position times time. Does that make sense? That's like the definition of position. And then of course to make this into a vector we have to remember to add, or not to add, but to multiply all of this with I hat. So there you go, that was the x situation. So it's going to be that plus, and now we have the y, which again will be r sub y at time 0 plus, and now we have to find out what the antiderivative of this term is, So it's going to be vz0, and we know that like this kind of term turns into this kind of term because we already had it over here, so we could just put that there. So because of this, we'll have plus vz at time 0 times t, right? And then, by the way, this is all going to be backwards. Like really you would write this one in front and this one last, but I'm just doing it like constant, then most intuitive thing, and then this is from the acceleration. That term, we derived that from the acceleration. So now we figure out what the antiderivative of this is. And by the way, I was allowed to split these up and find the antiderivative of both of them because it's basically the sum rule. But also we could find the antiderivative of these two at once. So this is the same thing as vz times 0 times t to the power of 0 minus gt. So we add 1 to all the powers of t. So we have t to the power of 1 minus g to the power minus something, the coefficient. So it's like coefficient times t to the power of 1 minus coefficient times t to the power of, now it's 2. Okay. And now we know that 1 times whatever this was, times whatever the coefficient was over here, 1 times that coefficient equals this. And so then we know that we just put this back over here. So I'm just going to do like a thing over here. Like it equals vz of 0. And then this, we know that 2 times whatever this was equaled negative g. So now it's going to be negative g over 2. Right? Right. So we have plus vz of 0t minus g over 2 t squared. And maybe you know a old idea that delta x equals x, like your x naught, like your original x, plus velocity times time plus acceleration over 2 times time squared. Maybe you know that. That looks very similar to this, right? This is our velocity at time 0 times time. This is our acceleration over 2 times t squared. And so this whole process that we're doing, this whole integration, is where this idea comes from. Sorry, hold on. What did I just get rid of? I don't know. But that whole process of integration is where this idea comes from. And we just proved it without even noticing. Okay, so it's our starting position plus our velocity times time plus plus our acceleration over 2 times time squared. So, by the way, that's how I'm checking to make sure that I got all this right, because it's all going nicely with what I've learned before. And so then this is this whole term times j hat. Okay, so this is our x, this is our y, and then our z, the z will look exactly like the x, right? Plus, so yeah, vz, not vz, sorry, rz, our original position. So position in the z direction at time 0 plus the velocity times time, so plus vz at time 0 times time, and that with k hat, and that is our position derived from acceleration. We started with acceleration as this term. We derove velocity, and then we derove position. And that's all just with integrals and derivatives. So there you go. That is it for today's lecture. Or it was like a few days lecture. I still have another one to do during the weekend. But yeah, that is the end of that lecture. Oh, I have another comment. Okay, so, if it was possible for things to go backwards in time, then maybe the negative variable would make sense, wouldn't it? Sometimes we get negative length too, haha. So again, negative length, we reject that, because there's no such thing as negative length. Negative time sometimes makes sense. For example, if I say that a ball has been falling for a few hours, and time 0 is like 10 meters, if I say we call time 0 at 2 hours ago, and a ball has been falling for 3 hours, obviously its starting position was higher than what it was at time t equals 0. So sometimes a negative time makes sense, but for most of the problem in like high school and stuff, negative time does not make sense. Anyway, guys, I'm wrapping up today's video. Good stuff. We still have another lecture to do before the weekend's over. Not going to do it today. It's also a crazy lecture. I'm not entirely sure what the professor was doing last lecture. It's like weird stuff. But anyway, I'm done for the day. It's been a pleasure. I'm going to end the stream. Adios.